Right, next up is Dr. Stephen Wright. Steve's a senior lecturer here at UE in avionics and aircraft systems. Although he's currently a lecturer, he's had 25 years in industry working for various companies, including Rolls-Royce, Airbus, and STMicroelectronics. So he'll be bringing that sort of practical side, I'm sure, to his talk on testing of avionics. Thanks.
Yes, thanks very much. Good afternoon. I'm Dr. Steve Wright, and welcome to UE, because I'm quite new here myself. And so in some ways, it's an interesting one here, because although I'm speaking as Dr. Steve Wright, what I'm talking about today is based more on my experience in the aerospace industry in the previous 25 years. In fact, about 18 months ago, I was trying to Google a website at Airbus, and it was blocked by the company filters, category education. So at that point, I knew that UE needed me, and even though I didn't know it, I think Airbus did too. So here I am, and some of the things I want to talk about today, really just glossing over, frankly, about testing in aerospace, and a lot of it's already said in the previous presentation, so I hope we don't contradict each other too much. I'm going to talk about really how we go about testing avionics and why we go about testing avionics as well. And in that respect, this the title of the conference today of intelligent testing perhaps doesn't really apply to aerospace very much, because in my opinion, there's not a lot of intelligence going into that testing strategy. So first things first, here's a piece of avionics. So the first thing we see about avionics is they look really, really boring, and they're black boxes with very expensive connectors on. Probably more expensive to buy one of those connectors than my mobile phone, things like that. But there's no doubt what they can do is spectacular, and they can make aircraft that are unflyable fly, and things like the A380 that I worked on for a long period of time, spectacular in the sheer amount of avionics and hence the sheer cost of the avionics that went into them. As I always say, it doesn't matter what you think about avionics software, it's like Windows 10. You're going to be using it anyway, mate, whether you like it or not. And you're going to be seeing more of it. And here's some numbers. And although there's numbers there, lines of code, and there's a blunt instrument if ever there was one. And yes, I acknowledge the beastliness of that metric of lines of code. But however you look at it, there's a lot of code, and there's getting a lot more of it going into avionics. Well, and it's worth noting those dates of first flight as well. So here we are at 2015, and it's still not in service. But yeah, the other thing to notice as well, 8 million lines of code. I'm sure a lot of people in here today, that's not actually a very large number. So the amount of code and the sophistication of these systems isn't particularly great. Certainly not compared to the mobile in my pocket, which has probably got tens of millions of lines of code contributing to it in itself. But this is where the cost comes in, this is where the complexity comes in, is in order to fly our avionics, we have to satisfy these guys. There is a sort of worldwide police. So it was really set up just after the Second World War as there was this explosion in aircraft all over the world, and there was globalization of the industry. And so there's a series of national certification authorities in each area. The big ones that we're always concerned on are the US ones and the European ones. And they work pretty much as a single organization. They pretty much rubber stamp each other's certification processes. And what they're there for, basically, is to make sure that it's safe for you to fly your aeroplane over my house without you crashing it on my house. I'm not particularly bothered about whether your aeroplane works or not. I'm just caring whether you can sell it, but whether it's safe. So how do they do that? They issue type certificates. In other words, a certificate to allow you to enter that person's airspace. And in order to get that certificate, you have to demonstrate that you've achieved minimal operational performance standards, and they're enforced by a handful of procedures. Those procedures themselves, you'd be glad to hear, aren't government organised, but you won't be so glad to hear that they're essentially organised by a cabal within the industry itself. So I don't know which is better or worse. But there's already been mention today of DA178 series, and I'm going to talk about that in a second. That covers the development of software for airborne systems. It's now got a sort of sibling standard called DA254, which is defining procedures for developing things like FPGA and configurable hardware and things like that. Not to be confused with hardware more generally. It's more about configuration control. And there's a couple of others as well. So here they are. That other one is DA160G. So, of course, there's a lot more to keeping avionics working and safe than just developing it correctly. There's the actual physical environment that has to exist in as well. And so there's a whole bunch of standards literally describe how you go about spraying salty water over your box and putting glow lamps on it and things like that to see whether it's going to survive. And then, not so surprisingly as well, also radiating it with electromagnetic interference and whatnot. But these documents, they're pretty much global standards, but they're not very techy. They really just go about defining a life cycle. I mean, we heard about some of the technical details of DA178 in the previous talk. But really what they're just doing is specifying the ubiquitous V model. Who's got a picture of a V model in their labs at work? Oh, blissfully few? Oh, Don, let's have a quick show of hands. Who has to obey some vague semblance of V model? There's a blunt instrument, and I've got an entire lecture on the manifold shortcomings of the V model as a development process. So what is the V model? There weren't so many hands went up. So it's this concept of as we go down one side, we have top-level requirements to a system, which are refined to a high-level design, and eventually an implementation at the bottom of the V. And then we climb up the other side, testing at different levels as well. So you can see the idea there is we're enforcing a very requirements-based testing process. And I think that's not so great, actually, because it encourages a culture of box ticking, and I saw a lot of that going on, and not enough that I've noticed at the first talk today, talking about investigative probing testing in order to deliberately break the machine. Far too much confirmation bias going on, in my opinion. Challenge me on that, if you will. But one thing it does do, though, is at least it links up this idea and introduces this concept of validation, where essentially checking that we're developing the right system. So, in other words, that's a process of forcing the user and the customer to confront what they're trying to achieve. And then there's a verification process that goes on with that, and that's got its own particular meaning in this world. Verification meaning checking that it conforms to that validated specification. And so it works vertically and horizontally. So, talking about software particularly today, I think, it's coming up a lot. This thing, DA178B, I think there's been several mentions of it in several of the talks already today, so a quick review on that. DA178C came out only 3 years ago, and here's the interesting point, is up till then, airborne software development had been controlled by DA178B, and that's been around for 20 years. And I remember what a PC looked like in 1992, and I can tell you can develop a lot more bugs a lot more quickly by 2012. And in fact, even then, DA178C is really only an incremental update of those standards, albeit introducing some newer concepts like formal methods, model-based design, and things like that. But even then, the thing to remember, it's really not particularly prescriptive. It's mainly just generally, it's kind of controls the overall process as well. So a little bit of a jargon buster there, just so these slides are self-consistent. some of the organisations that write and enforce these documents as well. And as I say, there's also this sibling as well, DO254, which came out in 2005, and which just goes to show how new the realisation that configurable hardware is in terms of it making a potential contribution towards the behaviour of the aircraft. And it covers all those sort of things like FPGAs and whatnot. Now, one thing, though, that all these standards do achieve, and that is defining what do we mean by good enough. Very interesting, zero defects. Zero known defects, exactly. Yeah, thank you. Very good point. One of the nice things about these sort of safety standards is, one of the key points it makes is we do not achieve, we cannot achieve zero defects, zero unknown defects. All we can do is work to a level of probability. And we do actually assign probability factors depending on the level of severity of the outcome. But everybody thinks in terms of avionics failing, leading to a complete disaster. That is actually just one category, namely catastrophic failure. It's all pretty obvious what that is, namely killing the passengers. But there's lower levels as well. I'm only going to go down to the next one down is hazardous. You get the interesting effect there is that hazardous it's defined as hazardous when you kill the crew. So if you look at the numbers now, we're actually allowed to kill the crew 100 times more often than the passengers. Although this does have practical application when you're building a freighter. Think about that. So yeah, those are the levels we're working to. We're not looking for perfection because we'll never achieve it. We're seeking good enough, and demonstrably good enough as well. And one thing that all these standards doesn't do is stipulate actual tools and actual methods and things like that. It gives the general properties that have to be investigated. So we're looking at MCDC and things like that in the previous talk. Excellent stuff. But there's a whole range of tools out there populating all these different niches along that V chart. So at the very top level, we might use things like UML. You've seen that. And then there are these specification tools like DAWs, and then good old Simulink and some coding, other coding stuff as well. There's SCADE, which is a sort of safety-critical version of Simulink, I'm going to call it. Anybody worked with SCADE? Quick show of hands. Yay. Yeah. Only one there. Surprised. But yes, plenty of tools out there. The big one is this thing called DAWs. So the first thing to do is gather your requirements and try and make some semblance of cross-referencing them to each other. And it has its competitors, but DAWs is pretty much the de facto standard. Then when you get down to the development phase, we've got this SCADE thing. It's quite an interesting one, actually. Things like ADA-based tools with some contract programming and things like that. Quite big in the Anglo-Saxon world, oddly enough. While, strangely enough, the French-speaking world seems to like SCADE. Cultural thing? Don't know. Oh, and a quick word from our sponsors as well. Tools such as your sign here, brought to us by TVS, thank you. So these are the sort of tools which are attempting to provide some sort of integration between all these methods at different levels of abstraction within the process. Thanks, Mike. Stuck that one in. So now we get down to that software unit testing. So now we're looking at the world that we looked at in the previous talk. Very good stuff. And the point I want to make here, though, is one of the things that did come along with DO178C was this concept of unit testing, where we're testing our modules, and usually outside the actual avionics environment. One thing I thoroughly approve of was the recommended use of more static analysis and formal techniques to get away from just this test basis. And I agree with that quote from Deanstra about how testing has its uses, but how do we test for coverage? How do we test for generic properties and things like that? But then we probably move on. This is the world I used to inhabit, very much so. Hardware in the loop test rigs, where we plug our avionics into a large bunch of models and simulated I/O inputs, which do all that money, about a couple of million quid's worth there, which was the particular one we're looking at there is the A380's fuel management system, which is an IMA-based system, so incredibly sophisticated, massive proliferation in complexity over the previous aircraft that Airbus had done, and hence the hardware in the loop rig that supported the testing for that had to increase in complexity as well. Incredibly expensive machine, but very, very useful, so that we could go into our next level of testing up, which was what we call an iron bird rig. So in other words, this would be a huge hangar somewhere out there in either Toulouse or Bristol in the UK, where we'd lay out all the systems for the aircraft, hydraulics, electronics, avionics, mechanical systems even, and rev them all up, power them up, and see what breaks. And very expensive, very slow, but it's the next best thing to go flight testing. And so there's an A380 going off on its production flight test. Hasn't even been painted yet. And of course, one thing about flight testing, eye-wateringly expensive compared to running software tests in the lab, taking sort of tens of thousands of dollars an hour to put a flight test engineer on station at 30,000 feet in order to run a handful of experiments. And it's dangerous. There's been 3 major accidents that I've been indirectly involved with, and there's been many more around the world by the larger and by other airframers as well. Everybody's heard about the A400M going in the other week. Absolutely shocking software disaster by the sound of it. And people were talking about badly installed software. I don't think so. The system should have been resilient to that bad installation. So that shouldn't have slipped through the testing. And Gulfstream had a similar disaster a few years ago, and Canadair have crashed its test aircraft as well. It's something I speak at from personal experience as well. I spent a few weeks flight testing myself in production, and I can confirm that flight testing, it's an extremely nerve-wracking experience, and it's not very productive either. You don't get a lot done. You spend most of your time getting on station, running a handful of very tentative experiments. So don't do it. Use everything you can to avoid it. This huge pyramid of smaller rigs, starting at the top level of those iron bird rigs that we were talking about, moving right down to software in the loop, on-desk testing. Do whatever it takes. So one of the things that it came up as well, I'm glad to see our numbers actually tie up as well, was one thing's for certain, you don't get a lot done. You don't get much coding done. This has come up over and over again in the context of safety critical. And yeah, this metric of about 10 lines of code an hour, 10 lines of code a day for your final product. And if you're billing somebody at 100 quid a man day, $100 a man hour, which is probably what the internal billing rate is at Airbus, plug those numbers into some of those lines of code metrics that we saw in the first slide, and you get to these eye-watering numbers. And that's why these avionics systems have got these phenomenal price tags with them. So we've got their full authority digital engine controller there from something that plugs into a Royce's engine. I think it might even be I don't know. Looking at $100,000 to $200,000 for something the size of a suitcase, and it's probably got less processing power than my mobile phone. Not great. So where do I think is going to go next? Hard to say, very hard to say. One thing for certain, it ain't going to happen quickly. I think there'll be more model-based design and testing, and that's something that's come up over and over today. So that's certainly something we'll agree on. something that Rod and I agree on as well, talking about formal methods and the use of and the acceptance of formal and static analysis techniques in order to provide this more thorough and in-depth coverage and testing as well, rather than just slamming tests at it. So what DO178D will look like is anybody's guess, but it's probably several years away even now. And so one of the questions people are bringing up, which I think is a very good point, is why do we need airborne software and airborne system standards specifically? That slide earlier said that we're deciding on our level of criticality, which is essentially whether you kill people or not, and then decide on your reliability and hence the required rigor within your development. So can't that just be applied to anything? It should be truly generic, in my opinion. And so the fact whether it's a steer-by-wire system on your car or whether it's the fuel management system on an A380, it's irrelevant. I think there's just industrial inertia, especially in aerospace. So I'll just finish up by a quick summary there. Avionics testing, in my humble opinion and my experience and my lengthy experience, isn't really driven by good, sound engineering rationale. In my experience, it's driven by certification and, to a lesser extent, commercial goals. In other words, by commercial, avoiding that incredibly costly flight testing and even expensive rig testing. And the other point is, at the moment, the consumer space and the automotive definitely leading the way in testing. And one of the things I'm hoping to do in my research here at the UE is trying to drag the test of avionics in aerospace kicking and screaming into the 1990s at least. So thanks very much. And I'll just say, can you see yourself in this picture, anyone? Have you got any questions? Thanks a lot.
Right, thanks, Steve. Have you got any questions for Steve? There's one at the back and come across there.
I'm from the automotive industry, and you're not the first person I've heard of, senior manager and stuff, that said that avionics industries are looking to the automotive industry for ways forward. And it's kind of scary because you've had this safety specs and so forth for decades, and it's only now coming to the automotive market with ADAS cars that see around them and brake automatically, that kind of thing. So yes, we're doing it, and yes, we're having to find innovative ways of doing it because we can't afford. No one's going to spend extra money on their car. We've got to bring it in, and we've got to have cars that cost the same. But it's a bit scary because you've been doing it for ages, and you're looking at us.
Yeah. Well, I mean, one of the things that might be said there is maybe you need to get your innovation in quick before the certification standards firm up well enough to actually shut down any innovation. The gag I always have is, first rule of aerospace is thou shalt not do anything for the first time. It's coming your way, mate, I suspect.
Yeah, that's been my worry at the moment, because at the moment we've just got specs in and we're innovating to put this thing in place, but it costs so much to change a comma in a spec, in effect, that once it's in place, it could stagnate, and we'll be in the realms of waiting for the next accident before things can change.
I do have one hope, though, in that at least you're starting from a clean sheet, in the sense that I do hope that they don't base the automotive standards on this whole series of aerospace standards, because they go back to the 1980s and the sort of tool-based and tool-accelerated engineering world. And so one of the things I do hope is that when the automotive standards do firm up, at least they'll recognize all these systematic, generally machine-based techniques like formal methods, model-based design, and things like that. So that's one of my hopes, is that at least there'll be a chance to, if you're going to set things in tablets of stone, you may as well base it on something a bit more well-founded than the sort of very paper approach that really was enshrined within these standards. Fingers crossed.
Okay. Just a few comments on what you were saying with regards to the generic standard. I might be heckled in the room if I say this, but in my mind, the generic safety standard is a IEC 61508, which is a standard which the rail standard and the automotive standard is based on. Having worked on the 178B previously as well, I prefer the aerospace standard because I find it's an easier standard to understand and work with. But I do agree with you as well that we're looking at model-based design and formal methods. And the formal methods, I would take it wider and say not just this is basic statistic analysis, but looking at languages like ADMB and some of the other Z and some of the other languages that exist is definitely going to improve the quality. So basically, when you define the requirements, at that stage you already flesh out a lot of the issues which there's random testing or I can't remember the word now you were using, but basically testing to try and find errors. Or in the formal methods, you would actually be able to identify issues much earlier.
It's really funny you should mention rail, actually, because and also event B and things. My doctorate was in event B and formal methods and things, and it's something that seems to crop up over and over again, that rail seem to be a long way ahead in terms of use of formal methods. And everybody, when I say that to people who are involved in rail, they'll go, oh my God. And we say, yep, this is as good as it gets, guys. You're the best. And so, yeah, maybe the answer is a fusion. If, God forbid, we could all actually create a talking shop and merge the best of everything. Very interesting that there's somebody there with something good to say about DO178C. Because from my side of the fence, obviously grass is always greener by the sound of it. And the rail and standards and these generic, as you say, these generic standards that exist seem like a good idea. So it's very interesting to hear people saying that, yep, they have their shortcomings. Doesn't surprise me at all. Very interesting. Thanks.
Question. Do you see any, what problems do you see with the proliferation of so-called drones or UAVs or federated airspaces and the level of testing that they have to undergo or certification levels that they have to go through?
That's a really interesting question, actually. And the interesting thing about UAV is that it doesn't necessarily make any difference, because the slide to go back to is that one about my DAL's, design assurance levels, where you'll see that the level of reliability that's required is just based on the outcome. Now, catastrophic can be defined as killing someone, and catastrophic also defined as killing somebody on the ground. So in that sense, if you've got a UAV that's going to be on station over a built-up area or something, those standards and those reliability requirements are just going to ripple right through to the UAV as if it was a manned aircraft, almost, or some of the systems as well. Well, conversely, if you've got a throwaway UAV that's going to be launched over the Pacific off the side of a ship or something and stooge around the Pacific, then we can throw all the safety standards that be required to protect the pilot away, obviously, at that point. And because we haven't got an on-ground situation. So in other words, the mission that defines the reliability level. In other words, how does it endanger people? The fact that you've got a pilot in there or not, it's effectively just another person. And most of the issues with UAVs, and the reason they're so cheap, is because there's just so much you can leave out. There's just whole subsystems of missing life support and things like that. But yeah, the actual levels that you're going to have to certify to. The fact that it's a UAV is almost immaterial. It's the level of reliability you've got to achieve for that UAV, which could be the same depending on that mission.
We don't have time for any more questions, so thanks very much.